In this episode, we will review groundbreaking papers that have shaped our understanding of Albert Einstein's revolutionary theory of general relativity and its profound implications for the cosmos. In 1916, Einstein published the first comprehensive paper on the general theory of relativity, titled The Foundation of the General Theory of Relativity, in the prestigious journal Annalen der Physik. This paper provides a comprehensive description of the theory and its implications. The theory of general relativity makes several significant predictions that have been confirmed by experimental evidence over time. Some of the most notable include the expansion of the universe, the Big Bang, the existence of black holes, and gravitational time dilation. In 1927, Georges Lemaitre proposed solutions to Einstein's field equations indicating an expanding universe, which were confirmed by Edwin Hubble's observations in 1929. This evidence supported the Big Bang theory and significantly influenced cosmology. The 1965 discovery of cosmic microwave background radiation by Penzias and Wilson further validated the expansion of the universe and the Big Bang. Black holes are regions of space where gravity is so powerful that nothing, not even light, can escape their pull. These entities, predicted by the theory of general relativity, have been validated by various astronomical observations. In 1939, scientists J. Robert Oppenheimer and Hartland Snyder suggested that black holes could result from the gravitational collapse of massive stars. The first candidate for a black hole was proposed in 1970 and confirmed by 1990. Gravitational time dilation is the effect where time slows down in stronger gravitational fields. In 1971, physicists Joseph Haffel and Richard Keating conducted an experiment to test directly the predictions of Einstein's theories of relativity regarding time dilation. They flew cesium atomic clocks, which are extremely precise time-keeping devices, on commercial airplanes around the world in both eastward and westward directions. After the flights, the clocks were compared to reference atomic clocks that remained stationary on the ground. The traveling clocks showed slight differences in elapsed time compared to the reference clocks, with the discrepancies matching the predictions of special and general relativity within experimental error. The results were published in the prestigious journal Science. The Haffel-Keating experiment was significant because it provided direct empirical evidence of Einstein's theories under real-world conditions. The fact that time itself could be warped by motion and gravity, and that this effect could be precisely measured, remains one of the most famous experimental confirmations of relativity. In 1966, C.W. Reitdijk, and later, in 1967, Hilary Putnam, put forth an argument based on the concept of relativity of simultaneity, a principle found in Albert Einstein's theories. This principle states that observers in relative motion will disagree on which events are simultaneous, each experiencing a now in a different slice of time. They suggested that for any observer moving relative to an event, the event's outcome exists in the observer's future, even if it has not been observed yet. This reasoning supports the notion that the world exists as a four-dimensional space-time continuum and endorses the eternalist view of time where past, present, and future are equally real. The Reitdijk-Putnam argument implies that the universe is deterministic. The future of any object is predetermined and unchangeable from the perspective of an observer in relative motion. According to this view, the entire history of the universe exists as a single, static, four-dimensional block of space-time, also known as the block universe. However, some critics argue that this deterministic conclusion depends on the definitions of past and future, and that alternative conceptions of the present could yield different conclusions about the nature of the universe. Despite this criticism, a majority of experts in physics support the original conclusion of the Reitdijk-Putnam argument, favoring the idea of a deterministic block universe. Nevertheless, this deterministic outlook seems to conflict with the probabilistic and indeterministic nature of quantum mechanics, the other cornerstone of modern physics. General relativity describes the universe as a smooth, continuous fabric of space-time, whereas quantum mechanics reveals a patchwork of discrete, probabilistic events at the subatomic scale. In 1957, Hugh Everett proposed an alternative interpretation of quantum mechanics to reconcile it with the deterministic reality implied by the block universe. His theory, formulated to solve the quantum measurement problem, laid the groundwork for the many worlds interpretation. According to this interpretation, each outcome of a quantum event generates its own distinct universe, reintroducing indeterminism into our conception of reality. This suggests that instead of a single predetermined history, a vast and potentially infinite array of parallel universes exist, with every possible outcome realized. In our next episode, we will examine the most significant papers discussing quantum mechanics and its implications.